Hello, everyone. Welcome to this week's Crunch seminar. Today we have one speaker. He's Aras Bacho. Aras studied mathematics for his bachelor and master's degrees at the Berlin Institute of Technology and Sorbonne University, formerly known as the University Pierre and Marie Curie in Paris. He completed his PhD in partial differential equations at Berlin, focusing on the non-smooth analysis of nonlinear evolution equations. Subsequently, he undertook a postdoctoral position at Ludwig-Maximilians University of Munich, where he contributed to the mathematical foundations of artificial intelligence. Additionally, he served as a long-term visiting researcher at ETH Zurich in the group led by Professor Siddhartha Mishra, concentrating in operator learning. His research interests include partial differential equations, applied functional analysis, calculus of variations, machine learning, and complexity theory. Aras, thank you so much for your time. And with this short introduction, the floor is yours. Whenever you can start whenever you're ready.
Yeah, thank you very much, Juan, for the very nice introduction and for the opportunity to give a talk in your prestigious Crunch seminar. Yeah, today I want to present some of my works that focuses on like deep learning and machine learning, or the mathematical foundation of deep learning, especially for solving PDEs. So we can start. So we know all that PDEs are fundamental in many areas like mathematics, physics, engineering, finance, also increasingly in AI. And I mean, they're fundamental for describing physical phenomena that can be described by the Navier-Stokes equations like fluid dynamics, or the heat equation for heat transfer, or evolution of derivative prices and with the Black-Scholes equation. So people have been working on numerical methods to solve these, in some cases, highly nonlinear and high-dimensional problems. So, however, these classical methods, such as finite element methods, finite volume, finite difference methods, spectral methods, and so on, they are in some cases very efficient, but also in other cases they suffer a lot from the curse of dimensionalities. They have sometimes long computation times, even because result from this curse of dimensionality, and there are other numerical instabilities. So there are pros and cons for classical numerical methods for certain types of problems, but there's not really like a universal method that are good, especially like nonlinear and high-dimensional problems are still a very high challenge. And so here, the hope is that maybe deep learning, since it has already shown like promising results in some cases, in many cases, in other areas also, computer vision and classification and so on, then people, of course, we hope that there also maybe can be used to solve PDEs. So let me define a deep neural network. A classical deep neural network consists of layers. Like it's a composition of layers. Each layer consists of an affine linear map given by this function and a nonlinear activation function rho, and then the deep neural network essentially is a composition of these layers, and that's more or less it. Especially for PDEs, there have been a lot of methods already been proposed for solving PDEs. Especially like very well known are these physics-informed neural networks. I think originally introduced by the group of Kaniadakis, so-called vanilla pin, the original pin, and then we have versions or variants of these pins given by the weak pin, variational pin. And then we have also this operator learning paradigm that instead of one instance, we try to learn here the whole operator. on infinite dimensional Banach spaces or Hilbert spaces. And here the very famous, very known operators on operator learning methods are the so-called neural operators and the deep operator networks. And we have also many variants of them. Then, of course, we have other kinds of neural networks that are more based on randomization, such as random feature neural networks. They are known to overcome this curse of dimensionality, while operator learning heavily suffers from this curse of dimensionality. And then also we have other methods like the deep Ritz method, which are based on some kind of minimizing a certain functional Euler-Lagrange, which leads to the Euler-Lagrange equations. And then we have also other methods that are not really based on deep learning, but more, for example, kernel methods or Gaussian processes methods, mostly led by Houman Owadi from Caltech. And then very recently, we have the very exciting new Kolmogorov-Arnold networks that are based on this Kolmogorov-Arnold representation theorem introduced by Tegmark this year. So in the first work, I want to show you some error estimates for physics-informed neural networks that we use to approximate solutions to the semilinear wave equation. So the general framework for PINs, for physics-informed neural networks, are given by a differential operator or like a set of equations. One is the differential operator operating on the solution. This is the first equation. Then the second equation is essentially represents the boundary condition. B here is the boundary operator, and psi is the boundary condition or the function on the boundary. And then we have also here an initial condition, and this is a very, very general framework. And for this general framework, we can define this physics-informed neural network. The original vanilla pin approach defines some residuals, and the main idea is to incorporate these residuals into the loss function and to minimize subsequently the loss function in order to obtain such a solution. So we have these residuals essentially, just defining for each of these equations the residuals given by the PDE, by the boundary condition and the initial condition. And then there's the simple observation that if we have a solution, then the residuals are zero. So if we evaluate these residuals at the solution, then we have zero. This is a key observation for physics-informed neural networks. So this allows us to define the generalization error. So the advantage here is that we don't really have to have data points, or in other words, we can generate the data points during the training, so we don't have to calculate in advance any solution with any other classical method. So this is purely model-driven approach. Also self-supervised learning called. And then the generalization error is just the sum of the L2 norms of these residuals. And based on this generalization error, we can define a training error, since in practice we cannot really work with these continuous integrals, not yet, maybe in the future. But in order to train on the computer, we have to discretize these integrals, and so we come up with the discretization of the domain, or we choose a discretization domain, and the certain quadrature rule can be used here to approximate these integrals, which then leads to these sums that are evaluated on these quadrature points. So, okay, and so based on these errors, we want to essentially based on this approach, we want to try to solve the semilinear wave equation. So let me introduce the semilinear wave equation. Here we have the nonlinear wave equation at the beginning, the so-called D'Alembert operator evaluated on U. Then we have a linear damping, and furthermore, we have non-linearity in U. And yeah, so this semilinear wave equation is important in quantum mechanics and can also describe other important, nonlinear, essentially nonlinear wave phenomena. And then we have here, so the equation is supplemented with, supplemented with initial conditions for the function and its time derivative. And we have here, for simplicity, a homogeneous Dirichlet boundary condition. This can be easily replaced by other kind of conditions, which only makes the analysis a little bit more complicated. And in order to guarantee a solution, so to work with these equations, we have to assume, or we have to make certain assumptions on these, on the function f and on the function a, as well as on the initial conditions, in order to guarantee a solution that we can work with. Not only a solution, but a global unique solution. And these assumptions are essentially that f has a certain f and its derivatives has a certain growth condition, which is given by this inequality. And also this existence result, or this approach is based on existence result of Nakao, in which he assumes that the dimension is smaller and equal than 5. But so the pin approach can, or our pin result can, of course, be applied to any dimension, assuming that there exists a solution. So if there is a solution, then our approach works. But this set of assumptions only make sure that that there's a solution we can work with, also in practice. So if we want to do numerical results, this guarantees the existence of a solution. And here typically this nonlinearity can be chosen by the absolute value of u to the power m-2 times u, where m is greater than 2. Okay, for this semilinear wave equation, there's a known result of Nakao from 1990 that essentially guarantees this the global existence and uniqueness of a solution. And so under certain regularity assumptions on these initial conditions on the functions u0 and u1, we obtain a global unique solution that is in this function space. So, and in particular, the solution is also in this Sobolev space HK plus 1 on this space-time domain. Yeah, so again, we don't have to assume all of this, but if we want to work with a solution, then we can make these assumptions. And then for the semilinear wave equation, there are natural residuals that we can define that are given by the initial condition, the boundary condition, and the PDE itself. These are the first 4. And then there are also, for proof-related reasons, we need to define 2 more residuals that can be derived from this from the second residual, so essentially the boundary residual. So we have the boundary residual for every time, and then we can take the time derivative and have the same condition. So this for the solution, it's also true that the residual, this residual is 0. And similarly, we can, for this initial condition, we can take the gradient and define this residual. So for numerical results, I think, or for practice, I think it's also even maybe makes hopefully the algorithm faster, converging to the solution, since we have more more conditions on the neural network, that it's forced to converge maybe faster.
Aras, I think that we have 2 comments on the
Sorry.
Suleiman, do you want to introduce yourself? Do you have any questions?
I just want to point out that for the error estimates, as the archive date suggests, our paper is the first one, just to mention.
Oh, okay.
The first one, sorry, on what?
Error estimates for deep learning methods.
Okay, sorry, is this for the semi-linear wave equation?
No, not for the wave equation. I accidentally put the chat earlier than
Oh,
expected.
okay.
So sorry.
Okay.
Yeah, sorry.
Yeah.
Okay. Okay, where's the... Yes, thank you for the comment. I didn't say who. I think you might be the first who derived, I think, error estimates, but lucky I didn't say anything about that. Okay, so we have now, and I'm happy that it's not for the wave equation. Okay, so we have here now defined the residuals, and now we can define in a similar way the generalization error, which is essentially just the sum of the squared of the residuals and the L2 norm. And then again, similarly, we define the training error by discretizing the integrals or applying a certain quadrature rule to the integrals. In this case, in our case, also for some numerical tests, we chose the midpoint rule. And so the midpoint rule allows us or determines the partition of the domain and the weights. So, and for studying a certain equation, I think Tim Derrick and Siddhartha Mishra also introduced a nice methodology of 3 questions related to pins, where they that are related to the total error, the generalization error, and the training error. And in their original paper, they studied the Navier-Stokes equation. So what they did, they asked these 3 questions and tried to answer them. So let me present these questions. So the first question is, given a tolerance epsilon, do there exist neural networks that depend on the parameters theta hat and theta tilde, such that the corresponding generalization and the training errors are small? Yeah, so this is the first question they ask. The second question is, given a physics-informed neural network with a small generalization error, like a small e.g., is the corresponding total error, so the total error is given by this difference and an appropriate norm, is the corresponding total error also small? So essentially, do we have some kind of continuous relation of the generalization error and the total error? And the third question is, given a small training error and a sufficiently large training size, is the total error again proportionally small? And so these 3 questions, also similar in the paper of Tim Derrick and Mishra, we have tried to answer these questions, and we have summarized them in a few theorems. So in the first theorem, we addressed the generalization and the training error. So under the assumptions of Nakao, we assume that U is a solution of the semi-linear wave equation with regularity k plus 1, with k larger than 3, and assume that omega is a subset of this rectangular domain and T positive. And then we have shown that there exist for each n, or for every n and capital N and small n, there exists a neural network with activation function given by hyperbolic tangent with 2 hidden layers. And the first layer has the width given by this terrible expression, and the second layer has a width given by this expression, such that we can estimate all the residuals by overall essentially by n to the power minus k plus 1. Yeah, this constant is highly nonlinear in D, and so also, let me say in advance, we don't overcome the curse of dimensionality here. yeah, it's highly nonlinear in D. So also this existence or this result is based on an approximation theorem, universal approximation theorem, also proven by Siddhartha Mishra in another paper, where they essentially showed that the function with such a regularity can be approximated by a neural network of that size in some H norm, in some Sobolev norm. And then given these error bounds, we can show that yeah, the generalization error essentially behaves like the ln of n times n to the power minus k plus 1. And similarly, we have an estimate for the training error given by the same rate plus the some rate that depend on the number of quadrature points for the spatial time domain, the space domain and the time domain, each approximating the domain of the PDE, the domain of the initial condition, and the domain of the boundary condition. So this is a nice result. And then in order to answer the second result, we have here assumed that U is already a classical solution of that is yeah, 2 times continuously differentiable, and then again we can bound the total error, and here we have the norm given by the Bochner-Lebesgue norm H10TL2. And so we essentially have the sum of the difference in the L2 norm and the time derivative in the L2 norm on the space-time domain. And so essentially we showed here that this total error behaves or can be upper bounded by something that is behaves like the linearly in the generalization error. So here we don't assume any let's say we don't use any kind of approximation theorem. It's just an estimation of the total error in terms of the generalization error. And similarly for the next result, we can derive a similar estimate, but for the training error. And additionally, we have these the discretization error essentially of the domain that are given by these 3 terms. And additionally, so these are the 3 results that essentially answer the question 1, 2, 3. So let me recap a little bit. So we have here the question, there exists a neural network that can make of a certain size that can make the generalization error and the training error sufficiently small. This is one. And then for the second one, we have shown that if the generalization error is small, then the total error is also small. And the third one, if the training error is small and we have a sufficiently large sample size or of the domain, then the total error is again small. And then based on these results, one can derive another result that essentially says that, or gives a guarantee that if we find the global minimum of the training error, then we can say that the total error behaves like epsilon. So for each epsilon, we have to assume that the neural network has a certain size. So these are the lower bounds of the size of the neural network. And then also we have a lower bound on the number of quadrature points. And if this is if this holds true, these lower bounds, and if we know that this neural network is a global minimum of the optimization problem, then we can guarantee this error. Yeah, but usually the difficulty is to find or to guarantee that we have or to assure that we have a global minimum. Yeah, so this was this part on the error bounds for the semi-linear wave equation. Are there questions so far?
Aras, this is Suku from Davis. I had a question on the existence. So how do you compare, like, when we talk about the universal approximation theorem, so then the existence is for just a single layer network, right? Primarily. So what you're doing is trying to understand what happens for a deep network?
Two hidden layer neural
For two hidden
network.
Okay. But then also then when you come to the two hidden layer, I noticed that in your number of the width of the network, the second one is also exponential, right? It goes n to the power d plus 1.
Yeah. It's
So
I mean, wait,
that doesn't really resolve the curse of dimensionality, right?
Here, this one, you mean?
Yeah.
Well, this is exponential in the dimension, so
yeah. So only in a dimension, you mean?
Yeah.
You said n is greater than 5, but you say n belongs to n. So what is n?
So this capital N?
Yeah.
So this is a free parameter that can be, so essentially, I mean, this parameter gives you the size of the neural network.
So it's finite, right? So of course.
Yeah.
So, so as d increases, that doesn't change per se.
Yeah, you can say that but I mean if d increases, then you see that these bounds increase. I mean, I haven't shown here the concrete dependence, but it's yeah.
So can you give but can you just give a sense of the order of the size of the network? Like a two layer. I mean, I know it's hard to quantify, right?
I mean, here, this is the width of the.
So for different choices of, K and N and all that, right? What would it be? Like, suppose you take a problem in, say, D equal to 2 or 3, for instance, right? So what is it telling us? To give a ballpark of, okay, this, the number of, if you take 100 by 100, a two-layer network, it should suffice, or is there something like that? Or it depends on many other factors, or I'm not sure how to articulate it.
I mean, the upper bounds for the width of the two layers is given by these quantities, right? So here they already encode the asymptotics. So if the let's say if the dimension increases, then you see that the second layer grows exponentially in n.
Yes. Yeah, sure.
So, and for the first one, it's only linear. So yeah, I'm not sure if I
I probably didn't ask it correctly, but I was just wanted to get a sense of, okay, you have a bound. So it's more about proving the existence that exists a network, right? That's basically the question you're answering in question 1.
Yeah, we just say that there exists a neural network of that size.
Right. And this wasn't known before, or because people have been using, I mean, there have been many theoretical papers before also, right? So how is it different from what people have done before, including Siddharth and other people, right, who have done some of the estimates for deep networks, right?
Well, this is, we use their universal approximation theorem. So,
okay.
Yeah, we haven't invented here anything new. We just showed that this methodology also works for the semi-linear wave equation.
Okay.
That
so
also
you're tailoring it to the semi-linear wave equation.
To the non-linear semi-linear wave equation. Yeah, so it's the so the semi-linear wave equation, because of the second time derivative and the non-linearity, has its own challenges. So yeah, but we haven't shown any universal approximation theorem, any new.
Yeah.
If that's the question.
Okay, one sort of, I don't know if it's related or unrelated. In general, for these problems which are time dependent, right? I mean, and especially being hyperbolic problems which have a causality, right? I mean, unlike, characteristic curves exist, unlike, say, parabolic problems or, elliptic problems, right?
Okay.
So how does one understand the notion of, because we are solving this, typically you're doing in a space-time formulation, like, you think of time and space, sort of in the same vein. But how does it, is there some notion embedded in the theory where there's a notion that, time t equal to t naught and time t equal to t naught plus delta t, should depend on the previous time or something like that, right? That things are moving forward, right? I don't know if my question was, clear, but
you mean that how does this hyperbolicity reflect
yes.
calculus, or?
Yeah, how does that reflect, because whether you're solving an elliptic equation or hyperbolic equation, the nature of the solution is very different, right? Based on the characteristics. So I was wondering, is it reflected somehow in the analysis also somehow? Or
okay. Yeah. I think well, I think not really, because we didn't really work on the existence part. We just essentially assumed that there's so I think maybe this is reflected in the main existence part, which was done by Nakao.
okay.
But not in I mean, I don't quite remember. Maybe there was some difficulty with the time for sure. I mean, but I don't quite remember if there was something like, you mean like a critical time point that makes the solution explode or something like that.
No, I'm assuming, assuming that the existence is, the exact solution is unique, let's assume, right?
Yeah.
Not assuming any instabilities and all that, right? But
Yeah.
just that in spite, because ultimately when you do hyperbolic problems,
Yeah.
until a wave hits a point, there's nothing happening there, right? I mean, so there's no, there's no u until a wave hits a certain point. If you have a pulse at the extreme, then nothing is happening in the center of the domain, for example, until the wave reaches that point, right?
Yeah.
So there cannot be a solution. It'll be zero, right? Until the wave hits a point, right? So that was the notion that, I was trying to understand better, right?
Yeah.
But it's okay. I mean, I don't want to stop you. You can go ahead.
I mean, yeah, I mean, so yeah, I think I need to think maybe deeper about the question, but yeah, we can maybe talk later about this. But thank you, yeah, for the question. I think I haven't really thought about, but I mean, for sure there were certain difficulties. One was, for example, that we couldn't derive this total error, so we couldn't choose the total error to be the L2 error. We had to take the sum of both, of the time derivative and the function. And then we could derive this estimate. Just yeah, maybe this goes into the direction. But yeah, maybe we can talk then afterwards. Thank you for the question. For the second talk, so we have seen here previously, we have seen these error bounds for physics-informed neural networks. And what are these error bounds essentially telling us? They tell us that how efficient physics-informed neural network is. Yeah. So how what can we expect if we do try to learn a solution using physics-informed neural networks? And then we already witnessed that for our approach, at least, it doesn't seem to somehow overcome this curse of dimensionality. And in this work, I want to present some results that go deeper into the solution of certain equations. In this case, the Laplace and the heat equation. So in this work, we showed that the solutions of the heat and the Laplace equation have some intrinsic complexity that are independent of any numerical method employed to approximate them. So if we, for example, take the solution of the Laplace equation, then this result tells us that the solution, or the general solution, not a particular solution, just the class of solutions, has a certain complexity that is maybe difficult to compute in general. Like maybe we cannot always expect to solve something efficiently on the computer. So this is this shows like a fundamental connection between functions and the digital computer that are based on the so-called Turing machine. So the Turing machine is the is a theoretical model of the digital computer. It's an idealization that helps us to study algorithms, or the complexity of algorithms. And so a Turing machine is essentially nothing else than some kind of finite state machine that performs certain or that performs manipulations or certain actions on this infinite tape of zeros and ones based on a set of rules. So, for example, one rule. So we have a sequence of rules, and then the first rule is maybe go two steps to the left and change the 0 to a 1. So this is a very, very basic model of computation, the so-called Turing machine. And this Turing machine is a very simple model that we can use it to essentially determine the complexity of certain algorithms or problems. And based on this kind of Turing machine, we can define what is a Turing computable number. So I think in the early 30s, Alan Turing introduced a seminal paper on the computable numbers, or on computable real numbers, where he showed or where he introduced this notion of computable number, and showed that there are only like countably many computable numbers. So he introduced this a definition that says a number x, like a real number, is computable or Turing computable if there exists such a Turing machine with input n and output gamma of n that approximates this number. And for each n, we have this error. So the Turing machine binary approximates this real number. And based on this notion, we can also define what the computable function is in a similar way. So again, for a function is called computable if there exists a Turing machine that can approximate this function on at each point with an error of 2 to the power minus 2. So this error is because we have a binary representation of numbers. So we want a binary convergence of the Turing machine to this function. And if this inequality is satisfied for all n in the natural numbers and x in a, b, then we say that f is a computable function. And so based on this notion of computability, we can also introduce complexity spaces or complexity classes. So complexity classes such as P and NP that allows us to let's say, classify certain algorithms or in particular in decision algorithms. So decision problems where one has to determine whether something is 0 or 1. We can put them into one of these complexity classes. And similarly, we can introduce complexity classes for these functions. So let me maybe also say what the polynomial time computable function is. So if we obtain this error after polynomial time of steps, we say that this function is polynomially time computable. Yeah, so if we obtain this error after a polynomial time of steps, so if, for example, we need exponential time of steps before we reach this error, then we are not polynomial time computable anymore. So here we are also interested in finding algorithms that can maybe compute a certain function in polynomial time. Yeah, so this is a different story than trying to find a numerical method that solves or computes a function. This is on the level of a Turing machine. So let me also recall the complexity classes P and MP. So P class P are all problems that can be solved, or decision problems that can be solved by a deterministic Turing machine in polynomial time. And we all know also the complexity class NP that contains all decision problems whose solution can be verified by a deterministic Turing machine in polynomial time. And then, of course, we have the class of NP-complete problem that contain all these decision problems in NP that can be reduced to every other problem in NP in polynomial time. In other words, NP-complete is the class of decision problems that are the most difficult to solve. And so these problems are, or these classes are defined for decision problems. Yeah, decision problems are problems that only requires an answer 0 or 1 as a solution. For example, for example, if the Sudoku problem. So if you solve the Sudoku, it's not known yet, but it's probably the case that there is no polynomial time algorithm that solves any Sudoku. But if I give you a solution, it's very easy for you to verify whether it's a real solution or not. So these are for example, a problem in NP, and also this particular problem, the Sudoku problem, is NP complete. And then we all know very famously that P is a subset of NP, and it's not clear whether P equals NP or not. And this is, again, an illustration of these complexity classes. So these are some examples of NP complete problems. I think I have to be a little bit faster. So similarly, we can define some complexity classes, FP and SharpP, that are useful or suitable for our problem. So here we can classify functions into complexity classes. So for example, the class FP contains all functions of this form that can be computed by a function oracle Turing machine in polynomial time. And the class SharpP contains all functions that enumerate the number of accepting computations of polynomial time function oracle Turing machines. Sorry, this sounds a little bit cryptic, but essentially, so SharpP is similar to NP. So while NP asks whether there is a solution, the class SharpP asks how many solutions do we have for a certain type of problem. Okay, and similarly, we can define FP1 and SharpP1 that are defined for functions that are only have as an input the unary strings, containing of finite strings with the zeros. Okay, this, I think I mentioned this. What is important here is also we know that FP is a subset of SharpP, but we also don't know whether they are equal or not. And in fact, if FP equals SharpP, this implies that P also equals NP. And so in other words, if FP is not is a real subset of SharpP, then there exist problems in SharpP that are not polynomial time computable. And this is also important for us. So we show that a certain solution of the, let's say, Laplace equation is in SharpP. So this means that there are no, I mean, if this is the case, this means that there are solutions that are not polynomial time computable. Okay, these are again some SharpP complete problems. And this is this result is essentially very important for our existence result. This was introduced or shown by Friedman in 1984. Juan, please stop me if I don't have time anymore.
Oh, no, please, please. Ideal is 1 hour, but if you need to take a few
Okay.
more minutes, it's fine. So
Okay.
you can keep going.
Thank you. Yeah, Friedman showed that that for polynomial time computable function, and these are very simple functions. So for a polynomial time computable function G, the integral, the indefinite integral is polynomial time computable if and only if fp equals sharp p. So this means that only integrating over a function that the complexity or the complexity class suddenly changes. So previously we had a polynomial time computable function, which is a very, very nice function, well-behaved function. And then if we integrate it to a certain point, then this function, this new function becomes suddenly, yeah, has a higher complexity, in other words. I mean, it's also wrong to say it's a higher complexity because we don't know whether these complexity classes are the same or not. So it suddenly jumps to another complexity class. Yeah, let's put it that way. And similarly, if we have a function, again, polynomial time computable function G defined on 0, 1 times 0, 1 to R, then the definite integral is also polynomial time computable if and only if fp1 equals sharp p1. And this is similar to this complexity class or problem. So we also don't know whether they are equal or not. And it's probably as hard as the P versus NP problem, or at least as hard, to show whether we have a strict inclusion or not. So I mean, this means, so what is the conclusion here? So if FP is a strict subset of sharp P, then this means there exists polynomial time computable function G such that this integral is not polynomial time computable. So, and this is also, so we can do whatever we want. We can come up with the smartest algorithm we want. We won't be able to, like on a Turing level, on the level of the Turing machine, we won't be able to compute this function in polynomial time. Again, on the Turing, on the level of a Turing machine, based on this definition I gave previously. Yeah, so let me come to our result finally. Having all these results ready, we can now state our result. So we just looked at the very, very simple equations, which is given by the heat equation and this Laplace equation, complemented the Laplace equation complemented with inhomogeneous Dirichlet boundary condition, and also for simplicity, and not only for simplicity, but we haven't been able to show it for the other domain. We choose here the domain as the ball, as the unit ball in RD. And given that, we have shown that for each dimension and for each continuous polynomial time computable function G, which is defined on the boundary, the solution to this boundary value problem is, first of all, computable in the sense of Turing. And we have shown that the solution is polynomial time computable if and only if sharp P1 equals FP1. So if this is a strict inclusion in F sharp P1, this means that for obtaining or the number of steps for obtaining an approximation of the solution with up to n significant digits grows non-polynomially in n. So if we want to have or to approximate the solution with n significant digits, then we need essentially non-polynomially many steps to obtain this error or this approximation. Again, if really these classes are not equal. And a similar result holds for the heat equation. If H, G, and F are continuous polynomial time computable functions, then for each T and L, we know first that the solution is computable in the sense of Turing. And then the second result is that the solution is polynomial time computable if this holds. The other direction was, we haven't been able to show yet. But this direction, and I mean, let me recall that this implies also P equals NP. So if FP equals sharp P, then then the solution is also polynomial time computable. And if not, then again we have the same implications as I mentioned before, that we have we would need exponentially many or non-polynomially many steps to compute significant number of digits for the solution. And this is again independent of any algorithm. So you can come up with any smart algorithm. This is this is independent of, so this is more fundamental on the level of a Turing machine. And then finally, if I have some time, I wanted to also talk about, or maybe, actually, let me skip this. I think this is a little bit too much. I think I skip this and then let's end it here. Thank you for the attention.
Okay, yeah, great, Aras. Thank you so much for this wonderful talk. This was really informative, and you have done a lot of work. Do we have any questions from the audience? Suleiman, you had a question earlier, right?
It wasn't really a question, actually. It was just comment about who did first this error estimates thing. Okay. So it's just a comment on this.
Oh, okay. Okay. Great.
So
just to point out that the regularity requirement for these error estimates and approximation by pin is a challenge. It's an open challenge, I think. So
again, sorry, can you?
This regularity requirement for error estimates in the pin approximation, I think it is open challenge, open question. So improving that and coming up with some different formulation is still an ongoing open issue, I think.
You mean for the related?
Because we are always assuming there is a solution with certain regularity and stuff like that, because it is required by the uniform approximation, universal approximation theorem. So those issues are still kind of open, like can be improved, I think.
Yeah, I mean, pins are not addressing the question of existence, right?
Exactly,
so far at least.
Yeah, but maybe you can come up with a different architecture, and then which requires less regularity or something. I don't know.
Yeah, but I think for that we need maybe like more guarantees.
Yeah, exactly.
For the optimization algorithm, if we can guarantee something like
exactly. Thank you.
Right, thank you, Suleiman. Suku, do you have any questions? I think he left already. Yeah, it looks like he left. Do you have any other questions from the audience? It looks like we do not. thank you so much, Aras, for this wonderful presentation. I'm going to actually Nasani, who's the co-organizer, she's going to upload the video to YouTube and maybe in a few days. And also I'm gonna ask George for inviting you to the seminar. And that will be all. Thank you so much, everyone, for your time. I hope you have a great weekend, and until next week.
Yeah, thanks a lot. Thanks a lot, man.